So let's get into that. So first exercise is name and describe the 4 use case examples of smart contracts from the lecture. So not too difficult. You just go into the lecture and take a look at the exercise, the slides. We had token systems in terms of we have what are tokens? So tokens are basically sub-currencies you can define yourself and send and transfer these to other parties. From a technical point of view, we will take a look at this in I think next week or in 2 weeks. But basically, it's more like an Excel sheet, an Excel sheet inside a smart contract, and you have methods to move these numbers around, and the smart contract ensures that the overall number of coins or tokens that are managed within this contract is not remains stable, so to say. So no inflation, no deflation, so to say. This is also commonly used for ICOs, so initial coin offerings, which was a big hype in 2017, where a lot of companies offered these tokens to get a revenue share or something like that. Then this was a valid approach. A second use case described in the lecture was identity and reputation systems. And in order to manage identities without a trusted third party, a smart contract can be used. So this is what you might have heard of. I'm pretty sure you did not heard of that. But if you look at decentralized identifiers, so these are DIDs, DIDs, decentralized identifiers, it's a proposal from the W3C, and verifiable credentials, also from a proposal from the W3C, World Wide Web Consortium. They propose to use blockchains as some form of immutable storage to basically keep track of your key material. So basically you store a public key on there, and you can refer to this public key via these decentralized identifier, and then you can, for example, log in with that information into online services, and you're entirely independent from any third party. So in comparison to log in with Google or log in with Facebook, for example, you're not dependent on Facebook, on the goodwill of Facebook, but the blockchain will be there and will provide the information about your account information. The third one was a decentralized autonomous organization. So the DAO is the organization that is controlled entirely by the multitude of smart contracts that are out there. And the idea is basically, so to say, that the stakeholders have a direct voting power there and make all decisions via this voting. Also, it could be something like a elected CEO could be voted in there. So more like a direct democracy approach. And also the last one is election and voting system. So smart contract can record votes in a non-modifiable way and can make sure that wallet owners do not vote twice. So that's something I'm not too sure about if that is really the perfect use case for blockchain. An example with so the smart contracts voting in terms of shareholders voting in DAOs or in other smart contracts, that's fine, but I would not allow a general election in Germany or in any other country to happen on the Ethereum blockchain, because there are so many incentives and there are so many things you cannot control, and there is so much at stake, and that it's really difficult to do that, especially when you have properties like Wahlgeheimnis, so the secrecy of your vote, so to say. That's really hard to build with with cryptography. So to really enable that, you cannot that a person who voted cannot prove to other party about the contents of its vote. That's really hard. So because that's something we really should care about in terms of that everyone is free to vote however they like, independent of the goodwill of other parties. Okay, so these are the 4 use cases. We talk about use cases in B. So there are many use cases for smart contracts. Think of 3 more and explain them as well. So I came up in the exercise sheet is basically a gambling system. So very good use case, Uli, very good. But it's true that it's one of the most used purposes on Ethereum. So gambling is a very big, lot of lotteries on there, pyramid schemes, Ponzi schemes, other games are out there just for the purpose of gambling. The second one is token exchanges. So there are some smart contracts out there which basically allow you to exchange tokens for other tokens. So you create, so to say, marketplaces for these tokens. And also a third use case, name registers. That's something, for example, if you remember or know the DNS, the domain name system, domain name service you use every day. For example, if you go to tum.de, the resolution from tum.de to the IP address of the server of tum is a DNS. And so decentralized systems could be exchanged with decentralized systems based on a blockchain-like infrastructure. Okay, the third one is find concrete addresses of contracts for 5 of the use cases from the previous 2 subtasks on the Ethereum mainnet. Explain briefly why a contract falls into a specific category. Hint, label cloud from Etherscan might help. I think we just take a short look into this label cloud, and we do not have to go over 5 use cases here. I think that's a little bit overkill, but just that you have an idea how that looks like and how it works. So basically, Etherscan labels smart contracts according to their to their functionality. I don't know if that is proposed by the users or if it's if they do it on their own, but you can see it a lot here. And then, for example, you have a lot of different categories, so to say. So we have a lot of collectibles. So if you look at collectible tokens, so they require you to log in. I don't have now my account here, but so to say, we can access these smart contracts here. And chain breakers, I don't know what that is, but you see here transactions going on, what type of ERC20 transactions happen there. You can look at the source code, so to say. There are a lot of labels here. So what else do we have? DAOs, for example, even dating. Wow, never heard of that for the first time. Energy sector, esports, stuff like that. So there's a lot of things going on here. My Crypto Heroes, that sounds like a game. So you can just take a look and daily action. I don't know. Take a look at that, and that's really the advantage here. It's everything open, it's available. Okay. Then we can, maybe let's talk a little bit about that, and before we go to the next exercise, because I think what we do now here is, or what you also do in the lectures, we just say, okay, that's a use case, and thousands of use case, and blockchain is good and great, and everything works, but that's not the case actually. So creating valid use cases or proposing valid use cases is really, really difficult. So there are so many issues with the technology in terms of how do we get data on chain, in terms of we need reliable oracles. So if you want, for example, this supply chain use case, all people talk about, we put our complete supply chain on the blockchain, and therefore we know everything and no manipulation and no and so all these proposed advantages basically built up on the assumption that you're able to include the data you have about these, about for example your box of, I don't know, fruits, that you have all this data, and that the data at the moment that it's getting inserted on the blockchain is actually reliable. And that's and this is the Oracle question. This is one from my perspective, one of the largest problems in Ethereum, that you have to, or in blockchain in general, the data you put on the blockchain needs to be tamper-proof. And this is not a blockchain problem, but it's a technical problem to design chips and to design hardware in a way that it cannot be tampered with. And that's something I also think is, if you, for example, have some kind of hardware that you cannot tamper with, then why do you need a blockchain? So, for example, this device would require some internet connection. It would require some signature mechanisms, and so this information that, for example, some temperature was not kept because your meat is getting bad, then you would need to. Then it would also be sufficient that this device is just sending you an email or sending some kind of ping to you and say, okay, temperature was not kept, or to all of the parties involved. Yeah. So the reason to deploy a blockchain and to use it, they have to be very good, because it is very expensive, it's very complicated, it's error prone. So we are just sitting here and saying, okay, this is a use case, that is a use case. That's very easy, but in nature or in practice, it is really getting very, very difficult. And if you wanna work on that, and if you wanna do that, you need to be really sure that you have the perfect use case. And from my point of view, the less you have to do with the real world, so to say, the better it is usable for the blockchain, but also it is less usable for the real world. So, for example, Bitcoin is a perfect example of this. It works perfectly. The money is safe. It's a digital money. Is it a store of value? I don't care right now. But for what it does, it works. And since 12 years, so that's valid. But obviously, apart from that, we do not have to input any data. We do not have some centralized parties we need to rely on. So that's really a core issue of this use case discussion here. Okay, let's move on. What is gas in the context of Ethereum? So I think I talked about this last week a lot, and the gas in context of Ethereum is obviously a way or a means to purchase for some instructions you execute. And so every function in the EVM has some kind of cost attached to it, and more complex functions obviously mean more gas. And you're also being able to set the price for your gas. So that's what the gas price is. When you say, okay, I want to pay 10 GWay for my gas, then that's up to you to define it like that. And your miner decides if he or she wants to include the transaction within the next block. So that's about the context of Ethereum, about gas here. So to continue, B, what happens with the spare gas if too much gas was provided for a transaction? Also, every gas that is not being used or every GWay that is not being used is basically refunded to the sender of the transaction, but basically it's not touched. So you only pay what you need. Anything on tweetback? No. Okay, let's take a look at the C. That's an interesting question, I think, because it gives you a little bit of feeling what's going on. And rank the following EVM instructions by their gas cost. Note the create instruction creates a new smart contract. And that's something I want to take a look together with you and discuss it a little bit, because we have a very nice document And that is the, you guessed it correct, the Ethereum yellow paper. Let's take a look. Ethereum yellow paper contains all information about Ethereum in a highly formal way, and it's really not your average afternoon lecture or book or text you read, but it's more like a, so I've read into sections that I find interesting, but apart from that, that's really a crazy document. And what we are interested in is the fee schedule. So that's what is important to us. And we wanted to take a look at the first one was, so first one was SHA-3. Oh, do like this. That's very good. Then we see it and we do not have to switch screens. Where is my Chrome here? Very good. So, the first one we want to take a look at is the SHA-3. So SHA-3 is, we can take a look here at the G, that's always the cost. And for example, we have G balance, amount of gas to pay for a balance operation. Balance is nothing we are interested in right now, but we would have to pay 400 gas for that. So we take a look and see if we find something like SHA-3, and there it is. So SHA-3 operation, so a hash operation, a hash function costs 30 gas here. The second method we are interested in is the push. And push is something I'm not sure if we find in here, because sometimes these push operations are, sometimes operations are more complicated or are calculated in a different way. And for example, you have some kind of pushes here defined in the W very low. We look at the W very low, it's defined in the G very low. And G very low means here we have 3. So we pay 3 gas for our push 4. Also for the later on we have this push 1, we pay the same amount here. Then we have a very interesting method, it's self-destruct. Let's take a look, and we have 2 things here. We have a R, very interesting, a refund given for self-destructing account, and G, so cost, self-destruct, amount of gas to pay for a self-destruct operation. So also very interesting to see that for an operation you receive a negative amount of gas. So in terms of you have to pay 5,000, but you receive 24. So in the end you have minus 19,000 gas on your gas counter, so to say. And so self-destruct basically gives you back 19,000 gas, but obviously that's something you have to consider. If you finish your transaction with negative gas, you're not getting a refund from the miner, so that's basically kept. And it can also, the refund you have is can always only be half of the amount you pay. So that always the miner receives some transaction fee, but you can reduce your transaction costs. And that's a that's a way to say there's an interesting concept here laying behind the self-destruct also option, also for this as clear. So there's also a refund when storage value is set to 0 from non-zero, because what people did is they invented a concept called gas token, and it's a token like tradable one, and it represents so to say gas. And the gas token can be destroyed, and if it's destroyed, it gives you gas. It gives you back gas. And what people did is they created a huge amount of gas tokens in times where the gas price was cheap. So this, what we saw before here, this gas price here was like 5 or 2 or 1. They created a huge amount of gas tokens, and now they can use these gas tokens to decrease their own transaction costs. So that's a really interesting concept. Can take a look at it. It's a little bit off topic, but that is what's going on there. So that's about the self-destruct. Then we have a jump. We have jump, jump, jump. I'm not too sure where it exactly is. Jump is I think I saw it here, yeah. So it's W mid is G mid, and therefore G mid is 8 gas. So then we have further functions. So create is definitely one that should also be here. Create is 32,000 gas, so that's a lot because you want to create a new smart contract. And we have this call, which is 700. Also, we have stop, which is very easy because I think it should be 0. W0 is stop, and G0 is 0, obviously. So if you stop, or if you halt the execution of a smart contract, then it's very cheap or for free. Some comment on tweetback is, doesn't the cost of push depend on the number of bytes pushed? Push 4 costs 4 times 3 gas. So I'm not too sure. So I think I have to check that. It would make sense, but push star seems to be any amount of push, and it's coined as W very low, and W very low has no further information there. So for example, with SHA-3, that there is more complexity in there, so the answer of 30 is not entirely correct. But for push operations, I don't see. I have to check on that. So it's a good remark. Thanks. Yeah, but apart from that, we can now sort this a little bit, and sorting it. No, that's wrong. Let's do a little bit of sortation here. So first of all, the cheapest one was definitely the self-destruct, because we get money back. So first of all, the self-destruct. Then we have the stop, which is free. Then we have the push, the 2 push operations, which are equally expensive. And then we have the jump. And then we have the SHA-3 with the 30 gas. And then the call. So call is when you call another contract and create the most expensive one in terms of when a new smart contract is created. Okay, continue here. In contrast to the transaction-based ledger of Bitcoin, Ethereum uses an account-based ledger to maintain the world state. In Bitcoin, double spend attacks are prevented by UTXOs. Once a UTXO is spent, it cannot be spent again, which creates a chain of coin ownership. How does Ethereum prevent double spend? And as I told you last week, there are 2 answers to that. So first of all, the double spending itself is always a consensus mechanism question. So Ethereum uses proof of work and therefore uses this to create one world state. But on a transaction level, as we only have an account-based ledger and we cannot spend unspent transaction outputs, we need to have a second mechanism or another mechanism with ensures that we have some kind of integrity in the system. And this is the nonce within the transaction. And I showed you that beforehand, but for the sake of completion here, we take a look again. If you have a transaction here, then you always see when you have a transaction, you include a nonce so that it cannot be mined twice. If you would not have a nonce, then you would not be able to determine if this transaction was created before or not, or was already included in the block. So therefore, that's important here. Also not to be confused with the miners nonce in Ethereum or in Bitcoin. So that's also very important here. So what you see here is, if you click to see more details, then we have a nonce. It is actually the first one from this contract, it seems. Okay. That's important here to know. So 2 questions, I think, from the from Tweakback to gas costs. Let's take a look at that. How did the authors come up with these gas costs? I'm not too sure. There are some really nice papers out there, scientific articles about how to exploit this. So what they did is basically they looked at the real costs in terms of execution time on machines and compared it to the execution times of, or to the gas costs of Ethereum. And they found some mispriced, actually the first transaction here. They found some mismatch between the time that it takes and the costs of the transaction or the cost of the operation. And actually there was an update on Ethereum or there are several updates enhancing these gas costs because there were some kind of attacks on the network which basically used this for malicious purposes to halt the network. So there was 1 week in 2017 where the network was completely unusable because some people messed around with these gas costs. Second question, if the operation and gas required is predefined, why do we need the start gas or gas limit? One can just specify the gas price, right? So we need the gas. The start gas is our gas price, so we need that for incentivization purposes, but that's something we discussed last week. And in terms of a gas limitation, in terms of a maximum gas, I think I confused the terms, sorry. I think start gas and gas limit is the same, but in terms of gas limit, that's the problem that you cannot really estimate it. So we can estimate it if we have a given state and we have the given transaction. But the problem is if the state changes and it's another state, then this gas cost can change. And that's something we need to account for, and that's something we need to ensure. So that's the point here. Okay, let's continue here. In Ethereum, there are 2 types of transactions. Whenever a wallet calls a method on a contract, a transaction is sent. Whenever a contract calls a method on another contract, a virtual message is sent, sometimes referred as internal transactions. Messages exist virtually and are not written to the blockchain. Why are messages not published to the blockchain? How could the blockchain be in the same state among all nodes without writing messages to the blockchain? So the key property of messages is that they are the result of the execution of a transaction. So if you take a look at a transaction and this transaction calls a smart contract and this smart contract calls other contracts, so to say, then these messages between these smart contracts are a result of the transaction of the externally owned account. And given the state of your network and the transaction that is created, you are able to replicate all steps And these steps involves the creation of these messages. So while messages are not explicitly stored on the blockchain, they are implicitly stored. So you're having a very, very easy time to see that these messages are created. And let's see if we find an example here on Etherscan here. I have no idea. Okay, no transactions here. I should have prepared some kind of example. There's some kind of, that looks good. So if we look here, that's a call from, that's the transaction. So this is a transaction from this address to this smart contract. And this created a internal transaction, which basically sent some ether from the smart contract. So that's 2x DAF is the smart contract to some third address. So that's very easy to look up in terms of the internal messages or transactions. We call them internal transactions or messages. So the messages is the official terms here. How could the blockchain be in the same state among all nodes without writing messages to the blockchain? So as I described right now, it's because of the implicit storage within the transaction. Question number 5. Name 4 reasons why a transaction that is sent to the Ethereum network might not get mined. Very good question, because we already had one example. So obviously the gas price could be too low. Also, what could happen is we could have a wrong signature. So as like in Bitcoin, a transaction gets rejected because of a wrong signature provided. Also, you could have a transaction which has not enough, where your base account does not You could have a account which has not enough funds to create a transaction. And also the last example I mentioned last week is that a transaction could consume more than 9 million gas and therefore could not be put into a block by a miner. So that could also be a reason, but that's really a corner case. I don't know if that really happens. I've never seen it, and yeah, obviously, because it doesn't show up in the block explorers. Name 2 different ways how a mined transaction can fail. So now we're not talking about rejection, but a transaction gets mined, gets included into a block, but fails. And there are 2 reasons. First of all, the first reason is running out of gas because your gas limit is set too low. Or it could be the case that you run into some condition that the smart contract executes a revert. So a revert is a opcode which basically reverts all the state, sets everything back to 0, so to the initial state, because you maybe have some kind of failed check. So in terms of if you have a modifier which says, okay, only admin and you not the admin, then that's a reason for a failure. Question C, why does a mined transaction that fails still cost gas? That's a very interesting question, and I think the idea here is, or I don't think the idea here is that you want to prevent people from sending transactions that are likely going to fail. So that's just an incentive, a disincentivation to create transactions which are going to fail. And obviously the miner has to check if the transaction fails or not. So they are getting rewarded for that, and it consumes all gas because it should be the maximum disincentivation. Okay, I think these are very valid answer here. 2 questions from Tweetback. Do nodes need to rerun all transactions to verify the integrity of the blockchain? This seems very computationally intensive in case there are complicated functions in the contract. The answer is yes. If you want to verify the integrity of the blockchain, you have to run all transactions. You have to check everything. Otherwise, you cannot really verify the integrity here. And this seems very computationally intensive in case there are complicated functions in the contract. So it is computationally very expensive. And so I've done this in terms of, we did a smart contract data analytics, and I did this on a machine which was a really powerful server. And I think we took almost a week to fully sync everything. So first of all, you need to get the data. That's a huge issue, because I think it's 300-400 gigabytes, which is not like a bulk download, but it's more like downloading in a P2P network. And also the whole recalculation stuff really takes a long time. So that's really an issue here, yeah. But not a lot of people do that. And yeah, really not cool. And transactions that becomes part of Uncle Block, can that be considered as failed transaction? No. So Uncle Blocks are basically meaningless for Ethereum. The only reason for Uncle Blocks to exist is to incentivize miners to work towards one longest chain and not to split up into a tree of chains, so to say. And all the transactions that are in there are basically irrelevant. You can think of them like orphaned blocks. So as in Bitcoin, they are not considered. The only thing that is considered is this mining reward. But this mining reward is not paid within the Uncle block, but the block that refers to the Uncle block basically pays that miner from this Uncle block this mining reward. So that's the idea. But apart from that, there is no really use in these Uncle blocks. Any further questions here? No. Okay, then we have a very nice question number 6. In this exercise, we take a closer look at storing data on the Ethereum blockchain. What is the difference between memory and storage in Ethereum? Memory is basically, so to say, a place where you can store data, which is only temporarily available during the execution of the smart contract. So if you need this, or if you don't need the data because it's like mathematical steps, then you can define it as memory, and it gets cleared after the execution of the transaction. And storage is a storage that is available throughout the time. So anytime you call the smart contract, the data will be there. Did I forget something? Yeah, so the memory is a non-persistent byte array used as temporal storage during the execution of a single transaction, and the storage is a data storage used by smart contracts, which is persistent between multiple transactions. Exactly. Question number B. At a very low level, storing data to storage is performed by the EVM instruction sstore. According to the yellow paper, the gas cost of a sstore operation is 20,000 gas when the storage value is set to non-zero from 0, and 5,000 when the storage value zeroness remains unchanged or is set to 0. Why is it cheaper to set a value to 0 than to set it from 0 to any other value? So the idea here is that if you take a look at the at such a variable, such a storage variable, then always this value is 0. So from beginning on, it is set to 0. And if you set it from 0 to non-zero, then you basically need additional space, and therefore this is much more expensive than if you set it from 0 to from another part to 0, from another value to 0, resulting in a and so to say that storage is getting freed up, and therefore it's only 5,000 gas. So that's the important part. So writing in blockchain, always very expensive. Removing some contents, not so expensive. Cheap or free reading. So if you have use cases which only read data from the blockchain, then very good. And now we have C, calculate an estimation of how much it approximately costs in US dollars to store 1 kilobyte of data on the Ethereum blockchain at the moment. For simplicity, consider only the cost of S-store operations and disregard everything else. Use current usual values from Etherscan for your calculation. So that's I think something we can sit down and do a little drawing. Let's look at my iPad. So we have a 1 kilobyte or KEB, and we have the S-store operation. And we know that we have equivalents to 20,000 gas. So one S-store operation, I think, stores 32 bytes. So that's also one S-store equivalents to 32 bytes. And if you want to do that, we want to store 1 kilobyte, you basically have to think about 24 bytes through 32 bytes. And who would have guessed this is 32 times? So we need 32 S-store operations. So when we now multiply this, so 32 times 20k, so this is 640. No, I'm stupid. I'm sorry. I dealt with too much numbers today. Obviously 640,000 gas is required. What was I thinking? So now we have the 640,000 gas. And now we need to take a look at the GY price. And we did this, I think it was, let's just assume for fun, 40 GY. So 40 GY times 40. Then we have 25,600,000 GY. So let's take this number and let's go into a very nice application that you don't have to use, but I'm using it because where did I put it? I had some window exactly for that reason. Exactly, so we have here our unit converter, and now we can put in these 25,600. So we see it's 0.0256 ether. And if we now multiply this by, let's take a look, what's the current ether price? 232. So 232 times 0.0256, we wind up about $5.9 US. So $5.9 US for 1 kilobyte of data. I think that's a shitload of money. That's crazy, and so that really shows you that it's really expensive. So let's take a look at the next one. I think we got some questions on tweetback. I have to check. Someone complained about 5B. That would be a valid answer for 5B. I would agree. Is the storage comparable to static variables in traditional object-oriented programming? So no, it's not. So static in the terms, so you can change them. That's people calling me. Not too good. I have to check that. I think it's not comparable. How would you store something by setting the storage value from non-zero to 0? Wouldn't that be removing something? Yeah, so you would basically overwrite the existing value within this field with 0. And how do we know that it saves 32 and not, for example, 64 bytes? So that's something I'm telling you. You can look it up on your own. But yeah, so the point of the exercise is not to confront you with a real life situation in your exam where I would say, okay, tell me about this store operation. You have no idea what's going on there. That's not going to happen. Yeah, but it's more like a sit down, do your research, Google it, and try to figure it out on your own. So this is also, I think, a very useful. It's very useful for you if you know how to find out this information on your own. Why didn't we factor in gas costs in the calculation in 6C? Why didn't we do that? I think we did that. So we have our, this is our operation, so to say, and this is our gas cost. So these 4D, this is our gas cost. And this is our 4D, 4DG way we assumed. And UC 2C, let me check what UC says. So if you would, we will take a look at this D, which tells you a little bit more about that. So we will try it right now here, and then you see there are additional costs here. So let's go to this. No. Also no, that's right. So Remix is an emulator to run and test Solidity code in browsers. Run the following test program. In the Remix emulator, empirically determine the real transaction cost of or gas cost of storing 1 kilobyte of data on the blockchain. To do that, copy and paste the code to Remix editor, compile the code and click the run section, click the blah blah blah. That's something I showed you before. And we can put in this data. Determine the price in US dollars as well. So that's something I did not test, and someone mentioned to me that it does not work, and I want to briefly explain why, and want to tell you how to run it. Let's see, where is my Remix? There it is. So that's now what you can see here. Fortunately, I can zoom here. So what you see here is this contract directly copied to to Remix, And the issue is we now want to deploy it. So we first compile it here, compiled, and then we can deploy it. And then we see this transaction, this contract here. And now we want to put in some byte array. And the issue is if we just do it what I told you in the exercise to copy it, and say put, then we get a transact to storage, error encoding arguments, error invalid to value. And then you can Google that. And then you will find up on this internet page, and they will tell you exactly that each argument needs to be 32 bytes long, and therefore we have to extend this. And this results in a very ugly answer for that. I have to check where I copied it. There it is. So unfortunately, the thing you now have to paste into your system is like this. So because we have to extend every single string, every single byte here with this extension. And if we now take this one and copy it into our Chrome and go back here and say we want to do that, then I failed for some reason. Why did it fail? It should be a valid hexadecimal. I tried it 2 minutes ago. I have no idea what I've done wrong, but I show you the transaction I did beforehand, and that was the transaction. Thank you very much. So now it works. Thank you very much. I'm just stupid. Today I'm not really on the top of my game. Okay, so if we look here, that's the transaction, and it really grinds. It's really not that easy to show it to you here. Okay, so we have this transaction. That's the last one here. And we have a transaction cost of 691,000. Execution cost is 664. And so that's the basic idea here. If you remember what we paid, we had 640,000 GWay was the execution cost of only the S-store operation, and then obviously we have some additional transaction costs here, so 691,000 gas. And if you put this again in our calculation, then you will see it's around $6 US. Okay, so that's about that. Try it out for yourself. I will also post this on. I will also provide this in the PDF under the video, so that it can easily access that. So there is one question: where did we specify the gas? So very good question. So we can take a look here and also define additional information here. So we should be able to say we can, exactly here. So this is our information. We can say if we wanna how we define the gas limit. So we could lower it For example, if we do 21,000 just for fun, then you will see base fee exceeds gas limit. So definitely we have an issue here. We cannot use this transaction because we provide too low gas. Also, what's very interesting, if we provide enough gas, but send some money with it, then we will also have a failure because this function is not payable. It has to be payable if we want to send money to it. So the call function should be payable if you send value. So that's also very very easy. Okay, let's continue with the sheet. Also, one question, I have also tried it with uint 32 and was far cheaper. Why? Also very good question. I have no idea. I'll try to figure it out and let you know. What additional cost factors are responsible that the real gas price determined in subtask T is higher than the estimation from task C? Name 3 factors. So that's also a very good question. What is, because we had some difference between the 690,000 and this 640,000. So where is this additional transaction fee coming from? And the answer here is that we first of all have the base transaction fee, so 21,000 gas is definitely an issue, and the other instructions are also there. So we have some kind of the function call, so to say. That's something that's definitely the case. And also the data input, if you put in data into your transaction, you have also additional costs. So that are the 3 additional transaction fees. But also the S-store is mostly responsible for this part here. Very good answer on tweetback. uint 32 takes up to 32-bit and bytes 32 takes up to 32 bytes. So that's definitely could be a valid reason for that. Thank you for Googling or for knowing that. Also, we have this question of the parity hack, and that's something I would not present today in the exercise because we're running a little bit out of time, and I would rather talk a little bit about the next exercise sheet. So all the answers is very, very nicely described in the solutions. And if we have time next week, we can I can talk about that again. But it's more like really it's not something to know or not something to really understand, but more in terms of to look at it and read up a little bit on the history of Ethereum and about the biggest hacks. Okay. So let's take a look at exercise sheet number 7.